12,000 years ago, the planet was shaken by a catastrophe of unprecedented scale. Waters rose from the ocean depths, swallowing up entire continents and civilizations. The ice that had accumulated over thousands of years melted in a matter of decades. The giant animals disappeared from the face of the earth as if they had been wiped out by an invisible hand. The surviving people preserved the memory of this flood in the myths and legends of all the peoples of the world. So what really happened to our planet in those distant times? Let's find out right now. Ancient myths of a global flood are scattered across the planet like shards of a broken mirror, reflecting the same tragic truth. From Sumerian clay tablets to the sacred texts of the Bible, from the Hindu Puranas to the legends of the Australian Aborigines, the same story of great waters engulfing the world resonates everywhere. In the Epic of Gilgamesh, written in Akkadian some 4,000 years ago, Utnapishtim recounts a divine warning and the construction of an ark. The gods had decided to destroy humanity with a flood, but a righteous man was instructed to save his family and animals. The storm raged for 6 days and 7 nights, until the waters covered even the mountain peaks. The biblical story of Noah is remarkably similar to the Mesopotamian tradition. Archaeologists have discovered that both versions originate from even more ancient sources. The Nippur tablet, dating to the 3rd millennium BCE, already contains all the key elements: a divine warning, the construction of a vessel, and the salvation of living creatures. The Hindu Puranas describe the Mahapralaya, the great dissolution of the world into water. Vishnu, in the form of the fish, Matsya, saves the righteous King Manu and the seeds of all living beings. Interestingly, Sanskrit texts point to the cyclical nature of these catastrophes, linking them to cosmic periods. In Chinese mythology, Emperor Yao struggled with a great flood that lasted for generations. The waters rose so high they reached the sky, inundating hills and encircling mountains. Only the wise Yu managed to tame the elements, digging canals and diverting the waters to the sea. Native Americans from Alaska to Tierra del Fuego have preserved tales of great waters. The Hopi tell of a third world destroyed by a flood when people forgot sacred laws. The Incas tell of how the god Viracocha flooded the earth, leaving only 2 people for a new beginning. Even in Australia, isolated from other continents for tens of thousands of years, Aboriginal people tell stories of a great rise of the ocean. Their legends describe a time when it was possible to walk to Tasmania before the great waters divided the lands. Modern folklorists count over 500 versions of the flood myth among various peoples of the world. Statistical analysis reveals a striking similarity in key elements: the suddenness of the catastrophe, its global scale, the connection with human sins or cosmic cycles, and the salvation of a few righteous individuals. Skeptics attribute this to the universality of human experience with floods. But defenders of the historical basis of the myths point to overly specific details that are difficult to explain by mere coincidence. Many legends pinpoint the precise timing of the catastrophe, the end of the last ice age. Archaeological evidence confirms that it was precisely 12,000 years ago that humanity experienced dramatic changes. Agriculture, livestock farming, and the first cities suddenly appeared. It was as if the survivors of a catastrophe were forced to reinvent civilization on the ruins of a lost world. The Younger Dryas catastrophe is one of the greatest climate mysteries in Earth's history, an event so sudden and massive that it radically altered the face of the planet within a few decades. About 12,900 years ago, as the Ice Age was drawing to a close, something unexpected happened. The world was rapidly plunging into icy cold. Temperatures in the northern hemisphere dropped by 10 to 15 degrees in just a few years, geologically overnight. Glaciers, which had already begun to retreat, once again encroached on the continents. Tundra-covered lands where forests had once been verdant. The dryas is an Arctic flower whose pollen was preserved in peat deposits from that time. Paleobotanists discovered it in layers where it shouldn't have been, too far south. These tiny pollen grains bore witness to a dramatic cooling event known as the Younger Dryas. Ice cores from Greenland reveal a striking picture. Isotopic analysis shows that the transition to a cold climate occurred incredibly quickly, possibly within just a decade. This rate of change is unprecedented in the planet's known climate history. Europe has become an Arctic desert. A kilometer-thick ice sheet has once again blanketed Scandinavia and northern Russia. Alpine glaciers have descended into valleys where vineyards now flourish. Permafrost has penetrated deep into the continent, freezing the land for centuries. But the most puzzling question remains the cause of this catastrophe. Milankovitch orbital cycles do not explain such abrupt changes. Solar activity was also within normal limits. Volcanic activity shows no significant spikes at this time. Oceanographers have proposed a theory of thermohaline circulation. A massive influx of fresh water from melting glaciers could have blocked the Gulf Stream, the warm current that warms the North Atlantic. Without this natural heater, Europe's climate would have become Arctic. Lake Agassiz, a gigantic glacial lake larger than all the modern Great Lakes combined, suddenly burst its ice dam. Billions of tons of cold fresh water gushed into the North Atlantic, disrupting the ocean's salinity and halting the circulation of warm currents. Geological evidence confirms the catastrophic floods of that period. The scablands of Washington state bear the scars of gigantic torrents that swept like mountain rivers. Erratics, huge rocks carried hundreds of kilometers by water, are scattered across North America. But the oceanic theory doesn't explain all the anomalies of the Younger Dryas. The cooling affected not only the Atlantic region, but also the Pacific coast, and even tropical zones. Glaciers advanced simultaneously in the Andes, the Himalayas, and New Zealand. Studies of ancient sediments reveal strange anomalies from that era. High concentrations of iridium and other cosmic elements, molten quartz microspherules, and nanodiamonds all point to possible extraterrestrial impact. Some researchers link these findings to the impact of a comet or asteroid. The Younger Dryas lasted 1 to 300 years, then ended just as suddenly. Temperatures rose 10 degrees Celsius in just a few decades. Glaciers began melting at an unprecedented rate, raising sea levels and flooding coastal plains around the world. It was at this turning point in history on the boundary between the Ice Age and the modern era that humanity underwent the Neolithic Revolution. Hunter-gatherers became farmers, and the first permanent settlements emerged. Perhaps the climate catastrophe forced our ancestors to invent a new way of survival. The melting of ice sheets and the rise of seas at the end of the last ice age represent one of the most dramatic geological transformations in the history of the planet. As Earth's climate began to rapidly warm after the Younger Dryas event, vast masses of ice accumulated over millennia turned to water at an astonishing rate. The Laurentide ice sheet, which covered most of Canada and the northern U.S., held a volume of water equivalent to a 50-meter rise in global sea level. The Scandinavian ice sheet added another 20 meters of potential rise. When these icy continents began to disappear, the planet's geography was forever changed. Marine geologists studying corals and marine terraces have discovered evidence of a catastrophically rapid rise in sea level. Barbados corals, which grow only at a certain depth, show that the sea rose at a rate of up to 4 centimeters per year, 20 times faster than the current rate. Isotopic analysis of foraminifera in deep-sea sediments reveals periods of particularly intense melting. Meltwater Pulse 1A, which occurred 14,000 years ago, raised the ocean by 20 meters in just 500 years. But even more dramatic was Pulse 1B, which occurred 11,600 years ago. This 1B pulse coincided with the final warming event after the Younger Dryas. Over 3 to 4 centuries, sea levels rose by 25 meters. Coastal plains, where people lived, and mammoth herds grazed, disappeared beneath the waves forever. Entire ecosystems disappeared into the abyss within a few generations. Continental shelves around the world bear the marks of this catastrophe. Off the coast of Australia, archaeologists have discovered the underwater remains of ancient Aboriginal sites. Stone tools and fire pits lie at a depth of 120 meters, indicating that this area was once dry land. Drowned river valleys are further evidence of the sudden rise of the ocean. The Hudson Canyon off the coast of New York was carved by an ancient river when sea levels were 100 meters lower. Submarine canyons in the Mediterranean Sea show that the Nile, Rhone, and other rivers once flowed across the dry seabed of today's sea. Particularly dramatic changes occurred in North America. When Lake Agassiz, a giant glacial lake, disappeared, its waters flowed in several directions at once. Some flowed into the Atlantic Ocean through the St. Lawrence Valley, and some into the Arctic Ocean through the Mackenzie River. The geological traces of these megafloods are still visible today. The channel of the St. Lawrence River was widened and deepened by the colossal flows. Sedimentary deposits in the Atlantic contain characteristic minerals carried from the Canadian Shield by these flows. Isostatic uplift of the Earth's crust added complexity to the sea level picture. Freed from the kilometers thick ice, the Earth's crust began to slowly rise. In Scandinavia, this process continues to this day. The land is rising by a centimeter per year in some regions. The Pacific coast of North America experienced particularly dramatic changes. The Cordilleran ice sheet, which covered British Columbia and Alaska, melted over several millennia. The fjords and islands of today's coastline formed precisely when the sea flooded the glacial valleys. The Antarctic ice sheet also contributed to the ocean rise. West Antarctica lost a significant portion of its ice, particularly in the Ross Sea region. Ice cores also show a sharp warming in the southern hemisphere, synchronous with the northern changes. The biological consequences were catastrophic. Coastal ecosystems adapted to stable sea levels for millennia disappeared within centuries. Mangrove forests, coral reefs, estuarine marshes, all were washed away or inundated by rising waters. Human populations concentrated along the coast due to abundant marine resources were forced to migrate inland. Archaeological evidence shows a sharp decline in coastal settlements during this period. Perhaps it was the need to find new food sources that prompted people to develop agriculture. The Black Sea catastrophe hypothesis represents one of the most fascinating attempts to link geological evidence with human memory of the Great Flood. This theory suggests that approximately 7,600 years ago, an event occurred that forever changed the geography of Eurasia and could have become the basis for the myths of the Great Flood. In the 1990s, Columbia University marine geologists William Ryan and Walter Pittman analyzed sediment cores from the Black Sea floor. Their discoveries revolutionized our understanding of the region's history. The deep sea sediments told the story of the catastrophic transformation of a freshwater lake into a saltwater sea. During the Ice Age, the Black Sea was truly a lake, a gigantic body of fresh water, isolated from the Mediterranean. The water level of this ancient lake was 150 meters lower than the current level of the Black Sea. Vast plains stretched where the sea waves now lap. Radiocarbon dating of mollusks in the bottom sediments revealed a sharp boundary. Below a certain layer are the shells of freshwater species, above which are exclusively marine ones. This boundary corresponds to a period of approximately 5,600 years BC, a time that unexpectedly closely matches the biblical chronology of the flood. When the glaciers began to melt, the Mediterranean sea level rose so much that the seawater breached the natural dam in the area of today's Bosphorus. The water gushed into the Black Sea basin with colossal force. Geologists estimate the falls were 200 times more powerful than Niagara Falls, a truly apocalyptic spectacle. The lake's water level rose 15 centimeters daily. The shores retreated 1.5 kilometers per day. In 1 year, the lake's surface area increased by 60,000 square kilometers. An area the size of Ireland was covered by water. The entire process took less than 2 years. Underwater exploration using deep-sea vehicles has uncovered astonishing structures on the Black Sea floor. At a depth of 90 meters, ancient shorelines, riverbeds, and even the remains of freshwater shells in their natural state were discovered. These findings confirm the sudden nature of the catastrophe. Particularly astonishing was the discovery of a 2,400-year-old shipwreck, perfectly preserved in the anoxic waters of the Black Sea depths. If wood can survive for millennia, then even more ancient artifacts must lie in the depths, awaiting discovery. Climatological data indicate that the region around the ancient Black Sea lake was particularly favorable for human habitation. Fertile plains, abundant freshwater, and a moderate climate provided ideal conditions for early agricultural communities. Archaeological finds confirm the presence of advanced Neolithic cultures in this region. Genetic studies of modern populations show traces of ancient migrations from the Black Sea region in various directions precisely during the period of the supposed catastrophe. Groups of people carrying specific genetic markers dispersed from the Balkans to Central Asia, possibly in search of new lands after losing their homeland. Linguistic data also supports this hypothesis. Many Indo-European languages retain similar roots for water, floods, and disasters. Some philologists attribute this to the shared traumatic experiences of the ancestors of Indo-European peoples. Critics of the theory point out that the scale of the Black Sea catastrophe was regional, not global. However, proponents respond that for ancient people, their region was the known world. A catastrophe that destroyed the civilization they knew could well have been perceived as the end of the world. Archaeological excavations in Anatolia reveal a dramatic shift in cultural layers precisely during the supposed flood period. Some settlements were suddenly abandoned, while others show signs of an influx of new populations. These may be traces of migrations triggered by the Black Sea catastrophe. Modern research continues to uncover new evidence of this dramatic event. Seismic profiles of the seafloor reveal buried river valleys and ancient deltas. Each new expedition adds detail to the picture of one of the greatest natural disasters in human history. The cometary impact theory offers a radically different interpretation of the events of 12,000 years ago. The hypothesis that fragments of a comet or asteroid collided with Earth, triggering a cascade of catastrophic consequences. This concept links the climate changes of the Younger Dryas, mass extinctions, and sudden cultural transformations of human societies. The theory's founders, geologists Richard Firestone and Alan West, noticed strange anomalies in geological layers dating back 12,900 years. They discovered unusually high concentrations of cosmic elements, iridium, nickel, and cobalt, in sediments across North America. Helium isotope analysis of these layers revealed an extraterrestrial origin for the material. The helium-3 to helium-4 isotope ratio is consistent with cosmic objects, not terrestrial rocks. These data indicate a massive influx of extraterrestrial material precisely during the onset of the Younger Dryas. The most compelling evidence came from the discovery of nanodiamonds, microscopic carbon crystals that form only under extreme pressures and temperatures. On Earth, such conditions occur either during volcanic eruptions or cosmic collisions. Volcanic activity was not abnormally high 12,000 years ago. The geographic distribution of these anomalies is striking. From Alaska to Mexico, from California to the Carolinas, a zone rich in cosmic elements and high-temperature impact products extends. This pattern is consistent with the trajectory of a comet that disintegrated in the atmosphere over North America. Computer modeling shows that a comet several kilometers in diameter, exploding at an altitude of 20 to 30 kilometers, could have created precisely this kind of impact zone. The energy of the explosion would have exceeded the yield of humanity's entire modern nuclear arsenal by thousands of times. The thermal consequences of such an event would have been catastrophic. Hot comet fragments falling to Earth could have sparked continental fires. Paleobotanical data indeed show a sharp increase in charcoal in sediments from that time, evidence of massive forest fires. The shock wave from the explosion could have destabilized the Laurentide ice sheet. The kilometers-thick ice sheet, subjected to sudden heating and shaking, began to rapidly melt and disintegrate. Billions of tons of cold, fresh water gushed into the North Atlantic, disrupting the thermohaline circulation. The atmospheric consequences included the release of enormous amounts of dust and smoke into the stratosphere. Sunlight was blocked for months or even years, leading to a sharp cooling, an effect similar to a nuclear winter. This is how proponents of the theory explain the onset of the millennia-long Younger Dryas. Astronomical data supports the possibility of such an event. About 13,000 years ago, Earth passed through a dense cloud of space debris associated with Comet Encke. The modern Taurid meteor showers are the remnants of this ancient swarm, containing large fragments up to a kilometer in size. Archaeological evidence also fits the picture of a cometary catastrophe. The Clovis culture, characterized by distinctive stone points, suddenly disappeared precisely at the onset of the Younger Dryas. It was replaced by different technological traditions, as if a cultural rupture had occurred. Critics of the theory point to the lack of direct evidence of impact craters of the corresponding age. Supporters respond that the comet could have completely disintegrated in the atmosphere, leaving no classic craters. Airbursts, similar to the Tunguska event, but thousands of times more powerful, could have produced the observed effects. Recent findings in Greenland ice cores have added further support to this theory. Ice layers corresponding to the onset of the Younger Dryas contain anomalously high concentrations of platinum, an element characteristic of asteroids and comets. These findings were obtained by independent research groups. If the cometary impact theory is correct, then the catastrophe of 12,000 years ago was not simply a climate event, but a cosmic catastrophe of planetary proportions. The collision with a celestial body triggered a chain reaction of changes that reshaped the face of the Earth and forced the surviving humans to invent new ways of existing in a changed world. The Caroline Bays and nanodiamonds represent some of the most intriguing geological evidence of a possible cosmic catastrophe in North America. These enigmatic formations are scattered along the U.S. East Coast from New Jersey to Georgia, creating a unique landscape that has puzzled geologists for decades. Carolina Bays are oval depressions, oriented in a single direction with remarkable precision. There are over 500,000 of them, ranging in size from a few meters to 11 kilometers in length. The largest, Lake Matamasket in North Carolina, is 11 kilometers long and 2 kilometers wide. Aerial photography first revealed the true scale of this phenomenon in the 1930s. From a bird's-eye view, a striking pattern became apparent. All the bays were oriented northwest to southeast, as if created by a stream of projectiles flying from the same direction. The edges of these basins are surrounded by ramparts of sand and clay ejected during their formation. Geomorphological analysis shows that the force that created them acted at an angle, ejecting the material primarily in a southeasterly direction. This pattern is consistent with an oblique impact. Geologists have proposed various explanations for the origin of the Caroline Bays. Hypotheses included wind erosion, dissolution of subsurface rocks, groundwater activity, and even the impact of whales in an ancient shallow sea. However, none of these theories explained the precise orientation of the basins. In the 1970s, geologist Henry Savage proposed the meteorite hypothesis. He suggested that the bays were formed by the impact of a swarm of small celestial bodies, possibly fragments of a disintegrated asteroid or comet. The impact trajectory explained the uniform orientation of the basins. Radiocarbon dating of organic remains from the lower layers of the bays yielded sensational results. Most of the basins formed between 10 and 15,000 years ago, a period that coincides precisely with the end of the Pleistocene and the beginning of the Holocene. Searches for cosmic elements in the sediments of the Caroline Bays yielded unexpected discoveries. Microspherules, tiny glass spheres formed at extremely high temperatures, were discovered in the sands and silts. The chemical composition of these spherules indicates exposure to temperatures exceeding 2,000 degrees Celsius. The most striking discovery was nanodiamonds, microscopic carbon crystals a few nanometers in size. These structures can only form under extreme pressures, typical of cosmic collisions or explosions. On Earth, such conditions are virtually impossible to achieve naturally. Carbon isotope analysis of nanodiamonds revealed anomalous ratios characteristic of extraterrestrial origin. The crystal structure of these diamonds corresponds to Lonsdaleite, a rare form of diamond found in meteorites. The geographic distribution of nanodiamonds extends far beyond the Caroline Bays. Similar finds have been made in similarly aged sediments across North America, from Alaska to Mexico. This vast impact zone indicates a continental-scale event. Spectral analysis revealed the presence of fullerenes, complex carbon molecules also characteristic of cosmic processes, in the bay sediments. These cage-like molecules contain helium atoms with an isotopic composition typical of cosmic objects. Paleomagnetic studies have shown that anomalies in the Earth's magnetic field occurred during the formation of the bays. Some samples show signs of exposure to strong magnetic fields, which could have been generated by the passage of a plasma cloud from a cosmic explosion. Supercomputer simulations have recreated a possible scenario for the event. A comet approximately 2 kilometers in diameter, exploding over the east coast of North America, could have created the observed pattern. Fragments of the comet, moving at an angle to the surface, carved out depressions and scattered cosmic material. The biological consequences of such an event would have been catastrophic for regional ecosystems. The sudden rise in temperature, shock waves, and radiation could have destroyed vegetation over thousands of square kilometers. Paleobotanical data show a dramatic shift in forest species composition during this period. Critics of the cosmic origin theory point to the lack of typical impact structures in shock minerals. However, proponents explain this by the characteristics of loose coastal sediments, which absorbed impact energy differently than hard rocks. The Caroline Bays and their associated nanodiamonds remain one of the most actively studied geological mysteries. Each new discovery either strengthens the hypothesis of a cosmic catastrophe or prompts the search for alternative explanations for this astonishing phenomenon of the American landscape. The megafaunal extinction at the end of the Pleistocene represents one of the greatest biological catastrophes in Earth's history, an event so sudden and massive that it forever changed the face of the continents. Giant animals that had dominated the planet for millions of years disappeared literally in the blink of an eye in geological time. Woolly mammoths, whose carcasses are still found in the Siberian permafrost, became extinct around 10,000 years ago. These colossal herbivores, reaching 4 meters in height, were perfectly adapted to the glacial climate. Their thick fur, subcutaneous fat, and behavioral adaptations allowed them to survive in the harshest conditions. The mastodons of North America disappeared around the same time. These ancient relatives of elephants inhabited forests from Alaska to Mexico, feeding on branches and leaves. Their massive tusks and powerful build made them virtually invulnerable to predators, all but the largest. Saber-toothed cats, Smilodon, represented the pinnacle of Pleistocene predator evolution. Their enormous fangs, up to 17 centimeters long, were the perfect weapon for hunting thick-skinned giants. The extinction of their prey meant their own demise. Megatherium, a giant ground sloth the size of a small car, slowly moved through the forests of South America. Their powerful claws allowed them to fell trees to harvest young shoots. Glyptodons, armored mammals the size of cars, were covered in bony plates and seemed invulnerable. In Australia, marsupial lions, rhinoceros-sized diprotodons, and enormous flightless drominid birds disappeared. In Europe, cave bears, cave lions, and giant Irish deer with antler spans of up to 4 meters became extinct. Radiocarbon dating reveals a remarkable synchronicity of these extinctions worldwide. Most species disappeared within a narrow time frame between 13 and 10,000 years ago. This simultaneity rules out chance and points to a common cause. Paleogenetic studies of mammoths have revealed a sharp decline in genetic diversity in the final millennia of their existence. Populations became increasingly isolated and sparse. The last mammoths on Wrangel Island became extinct just 4,000 years ago. Isotope analysis of megafauna bones reveals changes in their diet immediately before the extinction. Carbon-nitrogen ratios indicate stress, malnutrition, and changes in available vegetation. The animals clearly experienced severe nutritional difficulties. Archaeological evidence points to a human role in this catastrophe. Paleo-Indian sites contain the bones of mammoths, mastodons, and other extinct giants. Stone points have been found between the ribs of skeletons, indicating active hunting of megafauna. However, the scale of extinction exceeded the capacity of the small human groups of that time. Mathematical modeling shows that even intensive hunting could not have led to the complete extinction of all species in such a short period. Climate change also doesn't fully explain the extinction pattern. Megafauna successfully survived previous glacial cycles. Moreover, many species were eurybiontic, able to adapt to a variety of environmental conditions. The cosmic catastrophe theory offers a unifying explanation. A cometary explosion over North America could have triggered continental fires, destroying the herbivore food supply. The release of dust into the atmosphere led to cooling and further vegetation decline. Radiation exposure from the cosmic event could have disrupted the reproductive functions of large animals. Their long reproductive cycles made megafauna particularly vulnerable to sudden demographic shocks. Ecological chain reactions amplified the initial impact. The disappearance of large herbivores led to the overgrowth of grasslands, which in turn altered local climate conditions. Predators, deprived of their prey, also began to die out. Some species survived in refugia, isolated areas with favorable conditions. American bison, Eurasian reindeer, and several other species survived the catastrophe thanks to their behavioral characteristics and ecological plasticity. The effects of the Great Dying are still being felt today. The planet's ecosystems have still not recovered from the loss of large herbivores. Modern landscapes are largely shaped by the absence of megafauna, which for millennia maintained open spaces and influenced plant distribution. Göbekli Tepe in southeastern Turkey represents an archaeological revolution that has forced us to rethink everything we knew about the origins of civilization. This monumental complex, built over 11,000 years ago, appeared seemingly out of nowhere in a world of hunter-gatherers, demonstrating a level of organization and craftsmanship thought impossible at the time. German archaeologist Klaus Schmidt, who began systematic excavations in the 1990s, discovered something unthinkable. Radiocarbon dating of the organic remains revealed an age of 9,000 to 11,000 years BC, 6 millennia older than Stonehenge, and 4,000 years before the advent of writing. The monolithic limestone columns reach 6 meters in height and weigh up to 50 tons each. These T-shaped pillars are skillfully carved from solid blocks of stone with astonishing precision. Their surfaces are carved with relief images of animals: lions, boars, snakes, scorpions, and birds. Geophysical surveys have revealed the true scale of the complex. Another 95% of the structures remain underground. Magnetometric surveys have revealed the presence of at least 20 ring structures, of which only 4 have been excavated. The overall size of Göbekli Tepe is comparable to the largest archaeological complexes in the world. Engineering calculations show that the construction of just the visible portion required the efforts of 500 people over decades. Organizing such a project requires a complex social structure, a labor supply system, and centralized management, all of which emerged in other regions millennia later. The quarries from which the blocks were extracted are located 100 meters from the complex. Archaeologists discovered partially hewn columns there, allowing them to study the techniques of the ancient craftsmen. They used stone tools to carve multi-ton blocks with astonishing precision. Transporting and installing the columns required complex engineering solutions. Marks on the stones indicate the use of a system of levers and inclined planes. Some blocks bear traces of ropes, suggesting the use of lifting mechanisms, which were considered a much later invention. The orientation of the ring structures strictly corresponds to astronomical directions. The main axes of the structures point to the rising and setting points of certain stars during the construction period. This testifies to the advanced astronomical knowledge of the builders. The symbolism of the Göbekli Tepe reliefs remains a mystery. Depictions of predatory animals, snakes, and scorpions create an atmosphere of danger and magical power. Some columns have anthropomorphic features, stylized arms and belts, as if depicting giant guardians. Particularly intriguing are scenes that some researchers interpret as depictions of cosmic catastrophes. One of the columns is carved with symbols that may represent objects falling from the sky and animals in a state of panic. Archaeological research reveals dramatic changes in the region's fauna precisely during the construction of Göbekli Tepe. Bones of wild animals are replaced by remains of domesticated species. The complex may have become the center of the Neolithic Revolution, the transition to agriculture and livestock breeding. Genetic studies of modern grains show that their domestication occurred in the Fertile Crescent region, where Göbekli Tepe is located. Wild ancestors of wheat, barley, and legumes still grow in the area surrounding the complex. The most mysterious feature of Göbekli Tepe is its deliberate filling some 8,000 years ago. The builders carefully covered the structures with tons of earth and stones, as if they wanted to preserve them for future generations. The reasons for this decision remain a mystery. A comparative analysis with other megalithic monuments reveals striking parallels. The Maltese temples, Stonehenge, and Anatolian complexes all demonstrate similar planning and construction principles as if their creators shared a common knowledge. The catastrophe theory suggests that Göbekli Tepe was built by survivors of a global cataclysm. The sudden emergence of complex technologies and social organization may be explained by the need to restore lost knowledge and establish a center for a new beginning for civilization. Modern research using LiDAR scanning and ground-penetrating radar surveys continues to uncover new structures. Each excavation season yields discoveries that raise new questions about the origin and purpose of this astonishing complex, which has transformed our understanding of human history. Ancient maps of a lost world represent one of the most enigmatic puzzles in the history of cartography, documents that seem to preserve the memory of a planet that existed before great climatic catastrophes. The most famous of these maps is the Piri Reis Portolan, created in the early 16th century by the Ottoman admiral and cartographer. The Piri Reis map, discovered in 1929 in the archives of the Topkapi Palace in Istanbul, depicts the west coast of Africa, the east coast of South America, and, most strikingly, the northern coast of Antarctica. The admiral himself stated that he compiled the map based on 20 older sources. A detailed analysis of the map by American cartographer Charles Hapgood in the 1950s revealed its incredible accuracy. The coastline of South America is depicted with astonishing accuracy, including river mouths that had not yet been explored by Europeans at the time the map was created. The map's most striking feature is its depiction of Antarctica without ice cover. The continent is shown with mountain ranges, rivers, and bays, which are now hidden under a kilometer-thick layer of ice. These geographic details were only confirmed in the 20th century through seismic surveys. Orontius Phineas's map of 1532 also depicts Antarctica as an ice-free land. The continent is shown in correct proportions, with the mountain ranges precisely positioned. The Transantarctic Mountains, Ellsworth Land, and other relief features are reproduced with remarkable accuracy. The Portolan of Yehudi ibn Benzara from 1539 shows the northern coast of Antarctica in detail that became known only after modern subglacial exploration. The map includes details of the Queen Maud Land coastline with an accuracy that astounds modern glaciologists. Philippe Bouache's 1739 map depicts Antarctica as two separate islands connected by a narrow isthmus. This configuration was only confirmed in modern times, when it was discovered that there are indeed two landmasses beneath the ice. The Mercator map of the Arctic from 1569 shows the North Pole as an open sea surrounded by 4 islands. Modern research suggests that such a configuration may have existed during interglacial periods, when Arctic ice coverage significantly diminished. A cartographic analysis of these documents reveals the use of spherical trigonometry, a mathematical method formally developed only in the 18th century. The projections used by ancient cartographers require complex calculations and an understanding of the Earth's spherical shape. The accuracy of longitude depictions on ancient maps is particularly striking. Determining precise longitude requires accurate chronometers, which were invented only in the 18th century by John Harrison. How ancient cartographers solved this problem remains a mystery. Paper and ink examination confirms the authenticity of most of the disputed maps. Radiocarbon dating and chemical composition of the materials match the claimed dates of creation, ruling out the possibility of modern forgeries. The sources cited by the mapmakers often refer to even more ancient documents. Piri Reis pointed to maps from the time of Alexander the Great and even earlier sources. Some references lead to the Library of Alexandria and its lost treasures. Comparisons with geological data show that the ice-free Antarctica depicted on maps could have existed at the end of the last ice age. Paleoclimatic reconstructions indicate the possibility of a significant reduction in Antarctic ice cover approximately 15,000 years ago. The pole shift theory, proposed by Charles Hapgood, attempts to explain these anomalies by the movement of the Earth's crust relative to the poles. This shift could have led to a change in climate zones and the temporary deglaciation of Antarctica. Critics point to possible distortions in the copying of the maps, and that some similarities may be coincidental. However, the sheer number of precise details, particularly those concerning Antarctica's subglacial topography, is difficult to explain by mere chance. Modern research using satellite technology and penetrating radar continues to confirm the details of ancient maps. Each new discovery in Antarctica's subglacial topography adds weight to the hypothesis that these maps preserve information about the world that existed before the last glaciation. The possibility of an advanced civilization capable of precise cartography in prehistoric times would revolutionize our understanding of human history. Ancient maps may be the last witnesses to a lost world, erased by past climate catastrophes. The submerged cities of India and Japan stand as silent witnesses to ancient civilizations lost to the seas due to catastrophic sea level rise. These underwater ruins challenge traditional notions about the origins of the first urban centers and force us to rethink the chronology of human history. Off the coast of Gujarat in the Gulf of Cambay, marine archaeologists have discovered the remains of a large settlement at a depth of 35 meters. Sonar surveys revealed regular geometric structures stretching 9 kilometers long and 2 kilometers wide. The size of this underwater city is comparable to the largest archaeological complexes of antiquity. Radiocarbon dating of organic remains recovered from the bay floor yielded sensational results. The finds are between 7,000 and 9,000 years old, making the Cambay ruins older than Harappa and Mohenjo-Daro, the acknowledged cradles of Indian civilization. Underwater exploration using remotely operated vehicles confirmed the artificial origin of the structures. Regular rectangular blocks, step structures, and the remains of paved roads leave no doubt that a developed urban center once stood here. Artifacts recovered from the seabed include ceramic fragments, stone tools, and semi-precious stone jewelry. Stylistic analysis reveals links to cultural traditions previously considered characteristic of much later periods of Indian history. Off the coast of Japan, the underwater monuments of Yonaguni are striking in their scale and architectural complexity. This complex off the coast of Okinawa includes pyramidal structures, wide terraces, staircases, and canals carved into solid sandstone. The discovery of Yonaguni in 1986 by diver Kihachiro Aratake shocked the archaeological community. The main structure stands 25 meters high and 100 meters long, forming a stepped pyramid with a flat top. Geological studies conducted by Professor Masaki Kimura of the University of the Ryukyus confirmed the artificial origin of many elements of the complex. The precise angles, straight edges, and the presence of clearly man-made details rule out a purely natural formation. Yonaguni's submergence dates are based on sea level rise curves after the last ice age. The complex would have been submerged approximately 12,000 years ago, when melting glaciers triggered a global rise in the ocean. Petroglyphs discovered on the walls of underwater structures include images of animals and geometric symbols. Some of the designs resemble the Jomon style, the oldest known culture of the Japanese islands, which may indicate cultural continuity. Archaeological parallels with land-based monuments in the region support the hypothesis of artificial origin. Megalithic complexes on neighboring islands demonstrate similar architectural principles and construction technologies. Skeptics point to the possibility that the structures formed naturally as a result of tectonic processes and erosion. The Ryukyu region is characterized by high seismic activity, which could create the illusion of man-made structures. However, detailed analysis reveals elements difficult to explain by natural processes. Regularly shaped round holes, the remains of columns, and traces of stone tooling indicate human intervention. Underwater exploration off the coast of Tamil Nadu has uncovered the remains of the port city of Pumpuhar, mentioned in ancient Tamil literature. The epic poem Silapathikaram describes this thriving trading center swallowed by the sea after a catastrophic flood. Multi-beam echo sounding revealed underwater regular stone structures that may be the remains of piers, warehouses, and residential areas of the ancient port. The depth of the ruins corresponds to sea level prior to the Holocene ocean rise. Paleogeographic reconstructions show that during the last glacial maximum, sea levels were 120 meters lower than today. The vast coastal plains, now flooded, provided ideal conditions for the development of early civilizations. Genetic studies of modern populations reveal traces of ancient migrations associated with rising sea levels. Haplogroups characteristic of coastal regions indicate inland expansion precisely during periods of glacial melt. Submerged cities may represent only the tip of the iceberg of lost human history. Most ancient settlements were located along coastlines rich in marine resources. Their disappearance underwater could have wiped out entire chapters of human civilization, leaving only fragmentary evidence on the seabed. The disappearance of Doggerland represents one of the most dramatic geological transformations in Europe's post-glacial history, the complete submersion of a vast continent that once connected the British Isles to the European mainland. This lost land, the size of modern-day Poland, disappeared beneath the waters of the North Sea over several millennia. During the last glacial maximum, 20,000 years ago, global sea levels were 120 meters lower than today. Enormous masses of water were trapped within continental ice sheets, exposing vast areas of today's continental shelf. Doggerland stretched from the east coast of England to the Netherlands, Germany, and Denmark. This low-lying plain was covered with rivers, lakes, marshes, and forests. The climate was temperate, and the rich ecosystem supported a diverse fauna and undoubtedly human populations. Fishing trawlers in the North Sea regularly uncover the bones of mammoths, woolly rhinoceroses, lions, and other Pleistocene animals in their nets. These finds indicate that the flooded lands were once home to a rich megafauna. Particularly significant are the finds of stone tools and other artifacts of human activity. In 1931, fishermen recovered a harpoon made from a deer antler, approximately 13,000 years old, direct evidence of human presence in Doggerland. Seismic surveys of the seafloor have revealed buried ancient riverbeds. The Thames, Rhine, Elbe, and other European rivers once merged into a single river system that flowed through the center of Doggerland and emptied into the Atlantic Ocean far to the northwest of today's shores. Analysis of bottom sediments tells a story of gradual flooding. The lower layers contain freshwater diatoms and pollen from land plants. Above them lie marine sediments, indicating the advance of saltwater. The flooding process was not gradual. Geological evidence points to a series of catastrophic events that accelerated Doggerland's disappearance. Around 8,000 years ago, a particularly dramatic episode occurred, known as the Storegga tsunami. The Storegga underwater landslide off the coast of Norway displaced approximately 3,000 cubic kilometers of sediment. This colossal landslide generated a tsunami up to 20 meters high that rippled across the entire North Sea. Tsunami deposits have been found in coastal areas of Scotland, where they lie 20 meters above sea level. Characteristic sand layers with seashells and peat bogs indicate a sudden and powerful flood. For the inhabitants of Doggerland, this tsunami was a catastrophe. The giant wave washed away coastal settlements and may have completely destroyed the land bridges between Britain and the continent. After this event, the flooding process accelerated dramatically. Paleobotanical studies reveal dramatic changes in vegetation. Pollen diagrams record the disappearance of forest species and their replacement by marine organisms. The birch and pine forests of Doggerland were lost forever. The isostatic uplift of Scandinavia, freed from its ice sheet, complicated the sea level picture. Northern regions rose, redirecting meltwater flows southward and accelerating the flooding of low-lying Doggerland. Archaeological models suggest the existence of advanced Mesolithic cultures in Doggerland. The abundance of water resources, game, and plant foods created ideal conditions for the flourishing of hunter-gatherer societies. Genetic studies of modern European populations reveal traces of ancient migrations that could be linked to the flooding of Doggerland. Haplogroups characteristic of this region spread along the perimeter of the North Sea. Linguistic evidence also supports the hypothesis of Doggerland as a center of cultural development. Some common elements in the languages of the British Isles and continental Europe may have developed in this lost region. Modern technology makes it possible to recreate a detailed picture of Doggerland. Three-dimensional modeling based on seismic data reveals a landscape of hills, valleys, lakes, and rivers, a truly lost world beneath the waves of the North Sea. The exploration of Doggerland continues using the latest methods of marine archaeology. Each new discovery adds detail to the history of this lost continent and its inhabitants, whose civilization was swallowed by rising waters at the end of the Ice Age. The disappearance of Doggerland was one of the most significant geographical changes in human history, forever dividing Britain from the continent, altering the migration patterns of animals and people, and wiping out an entire chapter of European prehistory. Meltwater Pulse Event 1b represents one of the best documented and catastrophic sea level rises in Earth's post-glacial history. This dramatic episode, which occurred 11,600 years ago, raised sea levels by 25 meters in just 3 to 4 centuries. Marine geologists discovered evidence of this event in corals off Barbados, which grew at specific depths and recorded the precise level of the ancient sea. Analysis of uranium-thorium isotopes in the coral skeletons allowed them to establish the precise dates and rates of sea rise with unprecedented accuracy. Oxygen isotope analysis of foraminifera shells from deep-sea sediments confirmed the global nature of this event. The ratio of oxygen-16 to oxygen-18 isotopes changed dramatically, reflecting the massive influx of fresh water from melting glaciers into the world's oceans. Stratigraphic studies of marine terraces around the world have revealed a synchronous rise in sea level. From Australia to North America, from Scandinavia to New Guinea, geological markers everywhere point to the same time of catastrophic flooding of coastal plains. The 1B pulse was triggered by the sudden collapse of the remnants of the Laurentide ice sheet in North America. This colossal ice cap, which covered much of Canada, reached a critical point of instability and began to rapidly disintegrate. Glaciological models show that the ice sheet's destruction did not occur gradually, but rather through a series of catastrophic collapses. Enormous sections of ice, several kilometers thick, fell into the ocean, creating icebergs the size of small countries. Paleoclimatic data from Greenland ice cores record sharp temperature fluctuations during Pulse 1b. Isotope ratios in annual ice layers indicate that Earth's climate system experienced extreme fluctuations. Sediment cores from the North Atlantic contain layers rich in debris, evidence of massive iceberg discharges into the ocean. These Heinrich layers precisely correspond to the timing of meltwater pulses, confirming the link between glacier collapse and sea level rise. Geophysical studies have revealed evidence of gigantic outburst floods during this period. Ancient riverbeds in North America bear the scars of flows thousands of times greater than modern rivers. The scablands of Washington state were formed by precisely such megafloods. Isostatic uplift of the Earth's crust in areas freed from ice cover added complexity to the sea level picture. While the global ocean rose, some land areas also rose, creating regional variations in flooding rates. Oceanic paleosalinity, reconstructed from isotope ratios in marine sediments, indicates a sharp freshening of the North Atlantic. The massive influx of freshwater disrupted thermohaline circulation, which could have affected the climate of the entire northern hemisphere. The biological consequences of Pulse 1b were catastrophic for coastal ecosystems. Mangrove forests, salt marshes, coral reefs, and other marine communities adapted to stable sea levels were inundated or washed away by rising waters. Archaeological evidence shows dramatic changes in human settlements during this period. Many Mesolithic coastal sites were abandoned, and new ones arose inland. Perhaps it was the need to adapt to new conditions that spurred the development of agriculture. Paleogeographic reconstructions reveal the scale of territorial losses. Vast coastal plains from the North Sea to Beringia disappeared beneath the waves. Land bridges between continents and islands were destroyed, altering the migration routes of animals and people. Modern analogs of this process can be observed in West Antarctica, where glacial streams show signs of accelerating melting. Studying Pulse 1b helps understand the mechanisms of rapid sea level change and their potential modern analogs. Mathematical modeling shows that the rate of ocean rise during Pulse 1b reached 4 centimeters per year, 20 times faster than today's rate. For coastal communities, this meant a retreat of hundreds of meters annually. Geochemical tracers in marine sediments record changes in ocean circulation and productivity. Disruption of established currents has affected the distribution of nutrients and oxygen in the ocean, triggering regional environmental crises. Meltwater Pulse 1b marked a turning point in the transition from the Pleistocene to the Holocene, from the glacial world to the current interglacial epoch. This event ultimately shaped the Earth's modern geography and forced humanity to adapt to radically changed living conditions. Magnetic field shifts and solar storms represent cosmic forces that may have played a key role in destabilizing Earth's climate 12,000 years ago. These invisible yet powerful phenomena can influence atmospheric processes, ice sheets, and even tectonic activity on the planet. Paleomagnetic studies have revealed dramatic changes in the behavior of the Earth's magnetic field precisely during the onset of the Younger Dryas. Magnetic minerals in sedimentary rocks and lava flows from that time show anomalous deviations from the normal dipole field. The Lachamp excursion, which occurred approximately 41,000 years ago, demonstrates how rapidly the magnetic field can change. Over the course of several centuries, the field's intensity dropped to 10% of normal, and the magnetic poles completed almost a complete revolution around the planet. Archaeomagnetic data from burnt hearths and ceramics show that the magnetic field experienced strong fluctuations 12,000 years ago. The direction and intensity of the field changed significantly faster than in modern times. Cosmogenic isotopes in Greenland and Antarctic ice cores record periods of magnetic field weakening. Carbon, beryllium, and chlorine are formed when cosmic rays impact the atmosphere. Their concentrations increase sharply when Earth's magnetic shield weakens. The weakening of the geomagnetic field has cascading consequences for the climate system. Increased cosmic ray flux impacts the upper atmosphere, altering the chemical composition of the stratosphere and influencing cloud formation. Svensmark's theory suggests that cosmic rays catalyze cloud formation by serving as condensation centers for water vapor. With a weakening magnetic field, the increased flux of cosmic rays could have led to a sharp increase in cloudiness and cooling. Radiocarbon dating reveals anomalous spikes in atmospheric carbon production between 14,000 and 10,000 years ago. These peaks may indicate both a weakening of the magnetic field and periods of increased solar activity. Dendrochronological studies of tree rings confirm the climatic anomalies of that period. Tree rings from trees that survived the Younger Dryas transition show dramatic changes in growth patterns, indicating sudden climate shifts. Solar activity may also have played a decisive role in climate change. Concentrations of cosmogenic isotopes indicate possible periods of both extremely low and anomalously high solar activity at the end of the Pleistocene. Proton events and sudden ejections of high-energy particles from the Sun could have had a direct impact on the Earth's atmosphere. Given a weakened magnetic field, such events could deplete the ozone layer and alter the planet's radiation balance. Extreme geomagnetic storms could have affected ice sheets through induced currents in the Earth's crust. Electromagnetic fields can affect the crystalline structure of ice and accelerate the melting and destruction of glaciers. Auroral activity during periods of magnetic anomalies could extend to low latitudes, bringing additional energy to atmospheric systems. Charged particles penetrating deep into the atmosphere could catalyze chemical reactions and influence circulation processes. Paleoclimate models show that even small changes in the solar constant or cosmic radiation patterns can trigger nonlinear processes in the climate system. These triggering effects are particularly noticeable during periods of climate instability. Tectonic activity could also be enhanced by cosmic factors. Tidal forces modulated by changes in the magnetic field can affect stress in the Earth's crust and trigger earthquakes and volcanic eruptions. Modern satellite observations show that the Earth's magnetic field is weakening at an accelerating rate. The North Magnetic Pole is moving at a rate of 50 kilometers per year, which could herald a new geomagnetic excursion or even a complete field reversal. Magnetosphere studies have revealed growing anomalies, particularly in the South Atlantic Magnetic Anomaly. This region of weakened magnetic field allows cosmic radiation to penetrate deeper into the atmosphere, creating localized climate effects. The combined effects of magnetic shifts and solar storms may have created a perfect storm of climate change 12,000 years ago. A weakened magnetosphere, an unstable sun, and a sensitive climate system combined to produce a dramatic reorganization of Earth systems and possibly catastrophic consequences for ancient civilizations. The role of volcanoes and supereruptions in past climate catastrophes represents one of the most powerful geological forces, capable of radically altering the planet's appearance in a short time. Although the period 12,000 years ago was not marked by major eruptions, volcanic activity may have played a significant role in the cascade of events that led to these climate upheavals. Paleovolcanological studies show that significant eruptions occurred in various regions of the world at the end of the Pleistocene. Ice cores from Greenland and Antarctica contain layers of volcanic ash and elevated sulfuric acid concentrations, indicating major explosive events. The Lacher Sea in the Rhine Valley erupted approximately 12,900 years ago, almost exactly at the beginning of the Younger Dryas. This eruption released approximately 6 cubic kilometers of material into the atmosphere, creating an ash column up to 35 kilometers high. Tephrochronological data show that ash from the Lacher Sea eruption spread across Central and Northern Europe. Layers of volcanic glass have been found in peat bogs from Britain to Poland, attesting to the scale of this event. During this period, powerful eruptions occurred at the Shivlush and Kluchevskoy volcanoes in Kamchatka. Volcanic deposits from that time contain abnormally high amounts of acidic glass, indicating the highly explosive nature of the eruptions. Iceland, located on the mid-Atlantic ridge, also experienced increased activity at the end of the Pleistocene. Eruptions beneath the ice sheet could have created particularly dangerous Jökulhlaups, catastrophic glacial floods. The atmospheric effects of volcanic eruptions include the release of massive amounts of sulfur dioxide into the stratosphere. Sulfuric acid forms an aerosol curtain that reflects solar radiation and leads to global cooling. Mathematical modeling suggests that a series of synchronous eruptions could have reduced global temperatures by several degrees. Such cooling could trigger a positive feedback loop through increased snow cover and surface albedo. A volcanic winter, similar to a nuclear winter, could last for several years after major eruptions. The blockage of sunlight disrupted photosynthesis, killed vegetation, and caused the collapse of food chains. Geochemical tracers in marine sediments show anomalously high concentrations of volcanic elements during the onset of the Younger Dryas. Elevated levels of vanadium, chromium, and other metals indicate increased volcanic activity. Ice core acidity increases sharply in layers corresponding to the transition to the Younger Dryas. High concentrations of sulfuric and hydrochloric acids indicate the release of volcanic gases into the atmosphere. Tectonic stresses resulting from isostatic changes during glacial melting could have triggered volcanic activity. The removal of the glacial load altered the pressure in magma chambers, facilitating eruptions. Underwater eruptions in the North Atlantic may have had a particular impact on ocean circulation. The release of hot gases and ash into seawater altered its density and temperature, disrupting currents. A modern equivalent of this impact was observed during the eruption of Mount Tambora in 1815. This event led to the Year Without a Summer in 1816, when crop failure and famine swept the northern hemisphere. The Toba caldera in Sumatra, which erupted 74,000 years ago, demonstrates the scale of the potential climatic consequences of supereruptions. This event could have resulted in a volcanic winter lasting several years and a genetic bottleneck in the human population. The Yellowstone caldera, although it did not erupt during the period under review, demonstrates the potential for supereruptions to trigger global climate change. Such events are rare, but their impacts can be felt for millennia. The interaction of volcanic emissions with cosmic factors could have enhanced climate effects. The weakened Earth's magnetic field allowed cosmic rays to more effectively catalyze chemical reactions in the stratosphere. Regional consequences of volcanic activity included acid rain, water pollution, and vegetation destruction. Ash flows could dam river valleys, creating temporary lakes and altering hydrological regimes. Paleobotanical data reveal a sharp decline in plant diversity in regions of active volcanism. Spores and pollen in geological layers from that time demonstrate a predominance of stress-resistant species. Although direct evidence of catastrophic supereruptions during the period 12,000 years ago is limited, the cumulative effect of multiple eruptions could have created a critical mass for triggering global climate change. Volcanic activity, acting synergistically with other factors, could have been one of the triggers for the great climatic catastrophe of the end of the Pleistocene. Atlantis and the memory of a lost civilization constitute one of the most enduring and enigmatic myths in human culture. The story of an ideal society swallowed by the sea as a result of divine wrath or a natural disaster. This myth, first recorded by Plato in the 4th century BC, may contain echoes of real events from the distant past. In his dialogues Timaeus and Critias, Plato describes Atlantis as a powerful maritime power that existed 9,000 years before his time. He claimed this information originated with Egyptian priests who preserved ancient records of forgotten civilizations. The geographical details of Plato's description are strikingly specific. Atlantis was located beyond the Pillars of Heracles in the Atlantic Ocean, an island larger than Libya and Asia combined, and surrounded by concentric rings of land and water. Plato's chronology places the destruction of Atlantis approximately 11,500 years ago, a time strikingly close to the period of climatic catastrophes at the end of the Pleistocene. This coincidence has led some researchers to seriously consider the possible historical basis of the myth. The technological achievements of the Atlanteans, as described by Plato, included a complex system of canals, powerful fleets, metallurgy, and monumental architecture. This level of development is consistent with the idea of an advanced civilization that could have existed before the Great Flood. Geological surveys of the Atlantic Ocean have uncovered underwater structures that some enthusiasts associate with the legendary continent. The Azores Plateau and other underwater elevations contain formations resembling man-made structures. Alternative locations of Atlantis place it in the Mediterranean, where dramatic geological events actually occurred. The eruption of the Santorini volcano approximately 3,500 years ago destroyed the Minoan civilization on Crete, a possible prototype for Plato's story. In Tamil tradition, Kumarakandam is described as a lost land south of India, swallowed by the ocean in ancient times. This legend contains striking parallels with the Atlantean myth, including an advanced civilization and a sudden submersion. Mu, or Lemuria, in the Polynesian and Theosophical traditions represents another version of the myth of a lost continent in the Pacific Ocean. Although such a continent is geologically impossible, the myth may reflect the memory of lands submerged by rising sea levels. The Dogon of West Africa preserved tales of the Nomo, creatures who emerged from the water and brought civilization. These legends include detailed astronomical knowledge and may represent distorted memories of contacts with an advanced maritime civilization. The psychological aspect of the Atlantis myth is linked to the archetype of lost paradise in the collective unconscious. Carl Jung viewed such myths as projections of human aspirations for an ideal society and fears of catastrophe. Geological evidence of a sharp rise in sea level at the end of the Pleistocene supports the possibility of the inundation of vast coastal areas where advanced settlements could have been located. Continental shelves around the world contain traces of ancient coastlines. Archaeological discoveries in recent decades have revealed the existence of complex societies much earlier than previously thought. Göbekli Tepe, underwater cities off the coasts of India and Japan, and megalithic complexes all point to the possibility of advanced civilizations in prehistoric times. Linguistic studies reveal common roots in flood mythology among peoples separated by oceans. This may point to a common source, an actual event experienced by the ancestors of all human groups. Genetic data reveals bottlenecks in the human population around 12,000 years ago. The sharp decline in genetic diversity may have been the result of a global catastrophe that wiped out most of humanity. Critics of the theory of a historical Atlantis point to the lack of direct archaeological evidence for the existence of an advanced civilization of the required scale and time. Most scholars view Plato's Atlantis as a philosophical allegory. However, the growing number of underwater archaeological discoveries is forcing a rethink of this skepticism. Submerged cities and megalithic structures on the seafloor may represent fragments of lost human history. Modern deep-sea exploration technologies are opening up new possibilities for searching for traces of ancient civilizations on the ocean floor. Satellite bathymetry, underwater robots, and new methods of seafloor analysis can reveal artifacts hidden underwater for millennia. The myth of Atlantis, regardless of its historical accuracy, reflects a profound human intuition about the fragility of civilization and the possibility of its sudden disappearance. In an era of global climate change, this ancient story takes on particular relevance as a warning about the consequences of environmental disasters. Sumerian accounts of the wrath of the gods represent the oldest written sources that may contain historical evidence of a catastrophic flood experienced by humanity in prehistoric times. These texts, written on clay tablets in cuneiform, predate biblical sources by millennia and may represent a more reliable retelling of ancient events. The Epic of Gilgamesh, in its most complete version from the library of Ashurbanipal, contains the story of Utnapishtim, who survived the Great Flood by the will of the gods. This Akkadian text, dating to the 7th century BCE, is based on much older Sumerian sources. The Nippur flood tablet, dating from the 3rd millennium BCE, represents the earliest known version of the story of the Great Flood. It tells of King Ziusudra, who received a warning from the god Enki about the impending destruction of humanity. The Sumerian king list mentions rulers who lived before the flood and who reigned incredibly long, tens of thousands of years. After the flood, their reigns shortened sharply, which may reflect changes in living conditions or the system of chronology. The Atrahasis, a Babylonian epic from the 18th century BC, contains the most detailed description of the causes of the flood. The gods decided to destroy humanity because of the noise that disturbed their peace, but also because of overpopulation and human moral degradation. Enlil, the god of air and storms, is the primary instigator of the catastrophe in most Mesopotamian versions. His decision to flood the world is opposed by Enki, the god of wisdom and fresh water, who secretly warns the chosen righteous one. The technical precision of the Sumerian flood descriptions is astonishing in its detail. The dimensions of the ark in cubits are given, the construction of the vessel with 7 decks is described, and specific types of resin for sealing the hull are mentioned. The chronology of Sumerian sources places the flood in the distant past, but does not provide precise dates in the modern sense. However, references to the end of one era and the beginning of another may correspond to the transition from the Pleistocene to the Holocene. The motif of divine warning is present in all versions, but the methods of receiving the information vary. In some texts, the god speaks through the wall of a reed hut, in others through dreams or visions, which may reflect different ways of interpreting natural omens. The description of the flood itself includes dramatic details. The storm lasts for 7 days and nights, the water rises to the heavens, and even the gods are terrified by the destructive power of the elements. These details may reflect the memory of a real natural disaster. Archaeological excavations in Mesopotamia have indeed uncovered evidence of ancient floods. Woolley in Ur, Malawan in Nineveh, and other archaeologists have found thick layers of silt interrupting cultural deposits and indicating catastrophic floods. However, these archaeological floods are dated to different periods and were regional in nature. None of them corresponds to the scale of the global flood described in the epic texts. The geographical details of the Sumerian texts indicate the author's intimate knowledge of the real conditions of Mesopotamia. References to specific rivers, mountains, and cities suggest that the legend originated in this region. Sumerian cosmological beliefs included cyclical destruction and regeneration of the world. The flood was viewed not as a single event, but as part of cosmic cycles, which may reflect the memory of recurring climatic catastrophes. The etiological function of myth explain the origins of the post-flood world and the establishment of new laws and customs. The survivors became the progenitors of a renewed humanity, having received wisdom from the gods. The ritual significance of flood stories was evident in New Year ceremonies, when the creation of the world was symbolically reenacted. These rituals may have preserved the ancient memory of real events in a sacred form. Parallels with other ancient traditions strengthen the hypothesis of a common source. Egyptian, Indian, Greek, and other mythologies contain similar motifs, which may indicate a common historical basis. The transmission of texts over millennia was ensured by scribal schools and priestly traditions. The high status of these texts in Mesopotamian culture facilitated their accurate transmission from generation to generation. The interpretation of Sumerian sources by modern Assyriologists reveals multiple layers of meaning. The texts function simultaneously as historical chronicles, religious teachings, literary works, and scientific treatises. The ability to preserve historical memory over millennia is confirmed by ethnographic research. Some oral traditions demonstrate remarkable accuracy in transmitting information about ancient events. The Sumerian flood evidence, when considered in the context of the geological and archaeological data on the climatic catastrophes of the end of the Pleistocene, may represent an invaluable source of information about the actual events experienced by humanity 12,000 years ago and preserved in the collective memory of the civilization. The genetic bottleneck theory suggests that the human population experienced a critical decline approximately 12,000 years ago, with the surviving small groups becoming the founders of all modern humanity. Molecular genetic studies reveal traces of this demographic collapse in the DNA of modern humans worldwide. Mitochondrial DNA, transmitted exclusively through the maternal line, shows a sharp decline in genetic diversity around the end of the Pleistocene. Phylogenetic analysis of mtDNA indicates that all modern humans are descended from a relatively small group of female survivors of the catastrophe. The paternally inherited Y chromosome exhibits a similar pattern of reduced diversity. Coalescence analysis shows that most modern male lineages trace back to the few surviving populations from the end of the Ice Age. Genomic studies reveal traces of ancient bottlenecks in various human populations. Statistical analysis of modern genetic diversity points to periods of sharp decline in effective population size in the past. Haplogroups, groups of related genetic lineages, show geographic expansion from a limited number of refugia following climatic catastrophes. Molecular clocks date these expansions to between 15 and 10,000 years ago. Eurasian populations bear traces of a particularly strong genetic bottleneck. Analysis of single nucleotide polymorphisms shows that all non-African populations descend from a small group that left Africa and survived subsequent catastrophes. Native Americans exhibit extremely low genetic diversity, indicating descent from a very small founding population. Genetic data support the model of small groups colonizing the Americas via Beringia at the end of the Pleistocene. Australian Aborigines and New Guinean Papuans also show traces of ancient demographic bottlenecks. Their genetic lineages trace back to small groups that colonized Sahul during a period of low sea levels. European populations retain genetic traces of Ice Age refugia in southern Europe. The Iberian, Italian, and Balkan peninsulas served as refuges from which post-glacial recolonization of the continent occurred. Siberian populations exhibit adaptations to extremely cold climates that may have evolved during the Younger Dryas climatic catastrophe. Genetic variants associated with fat metabolism and thermogenesis show signs of strong selection. Demographic modeling based on genetic data estimates the minimum human population size during the critical period at several thousand breeding individuals. This population size is on the brink of extinction for large mammals. Comparisons with other species show that many large mammals experience similar genetic bottlenecks at the end of the Pleistocene. Mammoths, cave bears, and saber-toothed cats all show signs of demographic collapse before their final extinction. Epigenetic studies reveal traces of stress in genetic lineages dating back to periods of climate catastrophe. DNA methylation can transmit information about extreme conditions across generations, creating long-term adaptive memory. Human immunological genetics reveals evidence of adaptation to new pathogenic threats in the post-glacial period. HLA-complex genes demonstrate diversification, which may have been a response to epidemics among the crowded surviving populations. Cognitive genetics reveals traces of selection on genes associated with learning and adaptation. Variants in FOXP2, CACNA1C, and other genes that influence cognitive abilities show signs of recent positive selection. Pharmacogenetic studies show regional differences in drug metabolism that may have developed as adaptations to local plant toxins in the context of a changed diet after the disaster. The population structure of modern humanity reflects ancient migration flows from Ice Age refugia. Genetic boundaries between populations often correspond to the geographic barriers of that time. Holocene population mixing has partially erased traces of ancient divisions, but phylogeographic analysis still reveals major migration routes and centers of diversification after climate catastrophes. Cultural evolution also shows signs of bottlenecks and founder effects. Linguistic diversity and cultural traditions exhibit patterns consistent with demographic reconstructions based on genetic data. Archaeogenetics, the analysis of ancient DNA from archaeological finds, is gradually filling the gaps between modern genetic data and ancient events. The genomes of people who lived during the transition period provide direct evidence of demographic upheavals. A synthesis of genetic, archaeological, and paleoclimatic data creates a coherent picture of human history during a period of global catastrophe. The convergence of independent lines of evidence strengthens the hypothesis that modern humanity is a product of survival after a planetary-scale catastrophe. The genetic bottleneck of 12,000 years ago may have been a defining moment in human evolution, when small groups of survivors were forced to develop new adaptation strategies, including agriculture, animal domestication, and the complex social structures that laid the foundations of modern civilization. Contemporary scientific debates about events 12,000 years ago divide the research community into two main camps: proponents of traditional gradual processes and adherents of catastrophic change theories. This fundamental split in the scientific community reflects deeper questions about the nature of geological and climatic processes on Earth. The mainstream position, supported by most climatologists and geologists, explains the events of the end of the Pleistocene through natural processes within the framework of well-studied mechanisms. Proponents of this viewpoint emphasize the role of Milankovitch orbital cycles, changes in ocean circulation, and the gradual melting of glaciers. Alternative interpretations are gaining momentum thanks to the accumulation of anomalous data that are difficult to explain within traditional models. Discoveries of cosmic elements, nanodiamonds, and other exotic materials in late Pleistocene deposits are forcing a re-examination of established ideas. The cometry impact hypothesis proposed by the Firestone West group has encountered fierce resistance from mainstream researchers. Critics point to the lack of convincing impact craters and the inconsistency of some geochemical data with the extraterrestrial impact theory. Counterarguments by proponents of the comet theory include the possibility of a craterless airburst similar to the Tunguska event, but thousands of times more powerful. They also point to a growing number of independent confirmations of cosmic markers in sediments of the appropriate age. Discussions about the rate of climate change reflect fundamental disagreements about the nature of Earth systems. Uniformitarians insist on gradual processes, while catastrophists point to evidence of abrupt transitions and nonlinear changes. The archaeological community is divided on the chronology of human achievement. Discoveries like Göbekli Tepe are forcing a rethinking of the capabilities of prehistoric societies, but conservative archaeologists prefer cautious interpretations. Interdisciplinary research faces challenges due to specialization and methodological differences between scientific fields. Geologists, archaeologists, climatologists, and astronomers often use different approaches and criteria of evidence, making it difficult to reach consensus. The problem of reproducibility is particularly acute in space marker research. Some laboratories confirm findings of nanodiamonds and spherules, while others fail to detect them in the same samples, creating a methodological impasse. Research funding also influences the direction of scientific debate. Traditional theories more easily receive grants, while radical hypotheses face difficulties in attracting resources to test their assumptions. The sociological aspect of scientific debate includes the influence of scientific authorities and academic hierarchies. Young researchers often avoid controversial topics for fear of damaging their careers, which slows the development of alternative theories. Publishing practices in scientific journals create additional barriers to unorthodox ideas. The peer review system can be biased against hypotheses that challenge established paradigms. Media coverage of scientific controversies often oversimplifies complex issues, creating the false impression that alternative theories are equally valid. Popularization of science can both facilitate and hinder objective examination of controversial issues. Technological advances are gradually providing new tools for testing competing hypotheses. Improved analytical methods, satellite technology, and computer modeling are opening up new avenues for research. International collaboration is becoming increasingly important for addressing global scientific issues. Coordinated research programs can overcome the limitations of individual groups and national scientific traditions. Ethical questions arise when discussing catastrophic scenarios of the past and their possible modern counterparts. Some researchers fear that catastrophic theories could be used to justify alarmist views on climate change. The philosophical foundations of the scientific method are also in question. Popperian falsificationism, inductive generalizations, and Kuhnian paradigmatic science offer different criteria for evaluating competing theories. Future research directions include more accurate dating of events, expanding the geographic scope of anomaly searches, developing new analytical methods, and improving paleoclimate models. The convergence of various lines of evidence is gradually tipping the scales toward a more catastrophic interpretation of the events of the end of the Pleistocene. The accumulation of anomalous data from independent sources is creating an increasingly convincing picture of a global crisis. The practical implications of scientific debates extend beyond academic disputes. Understanding the mechanisms of rapid climate change is critical for assessing current climate risks and developing adaptation strategies. A synthesis of alternative approaches may prove more productive than competing schools of thought. The integration of gradual and catastrophic mechanisms into a unified theory of terrestrial processes represents the most promising direction for the development of science on the Earth's past. Could this happen again? This question is particularly pressing in the era of modern climate change and a growing understanding of the fragility of Earth systems. Analyzing current trends through the lens of catastrophic past events reveals troubling parallels and potential threats to human civilization. Current rates of glacier melt exceed those of most periods during the Holocene. The Greenland and West Antarctic ice sheets are showing signs of accelerating destabilization. Ice streams in Antarctica are moving increasingly faster, and subglacial lakes indicate processes that could lead to a sudden collapse. The thermohaline circulation in the Atlantic is showing signs of slowing, reminiscent of conditions preceding the Younger Dryas. The Gulf Stream is weakening due to the influx of fresh water from melting glaciers, which could trigger a cascade of climate change in the Northern Hemisphere. Earth's geomagnetic field continues to weaken at an accelerating rate. The North Magnetic Pole is shifting at a rate of 50 kilometers per year, and the South Atlantic anomaly is widening, creating gaps in the planet's magnetic shield. Solar activity is entering a period of possible long-term minimum, similar to the Maunder minimum of the 17th century. A weakening of the solar magnetic field could increase the flow of galactic cosmic rays impacting the Earth's atmosphere. Volcanic activity across the planet is showing signs of increasing. The Yellowstone caldera, the Phlegraean fields in Italy, and the volcanoes of Iceland and Kamchatka are all showing increased seismic activity and underground deformations. Astronomical threats include the possibility of collisions with asteroids or comets. The Torrid Stream contains kilometer-sized objects, and Earth periodically passes through dense regions of this space debris. Man-made factors add new dimensions to natural risks. Industrial emissions, nuclear arsenals, genetically modified organisms, and artificial intelligence create threats unprecedented in the past. The interconnectedness of modern civilization makes it particularly vulnerable to cascading failures. Global supply chains, electronic communications, and financial systems can collapse from relatively localized disasters. Population pressure places additional strain on planetary systems. A population of 8 billion is 2 orders of magnitude greater than the population at the end of the Pleistocene, meaning far greater potential losses in the event of a global catastrophe. Urbanization is concentrating populations in megacities, often located in vulnerable coastal zones. A sea level rise of just a few meters would affect hundreds of millions of people living in river deltas and low-lying areas. Biodiversity is declining at rates comparable to the great extinctions of the past. The 6th mass extinction has already begun, and its acceleration could lead to the collapse of ecosystems on which humanity depends. Climate models predict the possibility of abrupt transitions in the Earth system. Tipping points include the collapse of ice sheets, the halting of ocean currents, the melting of permafrost, and changes in monsoon systems. Geoengineering projects proposed to combat climate change could have unforeseen consequences. Solar geoengineering, radiation management, or massive alteration of the planet's albedo carry the risk of unpredictable climate shifts. Sociopolitical instability can be exacerbated by climate stress. Droughts, floods, and crop failures trigger migration, conflict, and the collapse of state structures, as has happened in past climate crises. Modern civilization's technological dependence creates new vulnerabilities. Space weather can disable satellites and electronic systems, paralyzing modern society to a far greater degree than would have affected prehistoric societies. The speed of modern processes exceeds the adaptive capacity of natural systems. While past catastrophes took centuries to unfold, modern changes occur over decades, leaving no time for gradual adaptation. Scientific monitoring and early warning give modern humanity an advantage over ancient societies. Satellite systems, seismic networks, and climate models can provide time to prepare for disasters. International cooperation and technological resources potentially enable more effective responses to global threats. However, political fragmentation and national interests often hinder coordinated action. System resilience can be enhanced through diversification, decentralization, and the creation of reserve capacity. Distributed energy production, local food systems, and autonomous communities can enhance survivability during global shocks. Historical lessons from past disasters show that survival depends on adaptability, cooperation, and the preservation of knowledge. Societies that were able to quickly change their strategies and technologies had a better chance of survival. The question is not whether a new global catastrophe will occur, but when and what kind. Planetary systems are showing signs of instability, and human activity can both accelerate and mitigate the impending changes. Understanding the mechanisms of past disasters is becoming critical to preparing for future challenges and ensuring the long-term survival of human civilization in a changing world.